new section is entitled Solutions of Linear Systems of Equations. In this video segment, we're going to learn how to solve linear systems of equations using matrices. First, we have to talk about when our matrix is in what is called reduced row echelon form. Let's formally write that. When is an n by n matrix A in reduced row echelon form. From now on, I'm going to write it like that. RREF. Okay. A matrix is in RREF form if it satisfies all of these three conditions. Excuse me. All rows that consist entirely of zeros, are at the bottom of the matrix. If there is exactly one row that has all zeros, it will be the last row. If you have exactly two rows that have all zeros, then the bottom two rows will be the rows that have all zeros. If you have three rows of a matrix in RREF form that consist entirely of zeros, then they can't be the first, second, and third row, and then the fourth row has some non-zero entries. No. The bottom three would have to be the ones that have all zeros. Going from left to right, the first non-zero entry, if any, there might not be. I mean, if the row consists entirely of zeros, there won't be. Reading from left to right, the first non-zero entry must be a 1. This one has a special name. This one is called the leading entry. Number 3. If I is bigger than j, the leading one of row I must be to the right, of the leading one for row j. That is, if row j has a leading 1 in the fourth column, and I is bigger, then row I must have its leading one, if it has one, in either column 6 or column 7 or column 8 or column 9. It must be in a column beyond the row I. As you go down in the rows, the leading ones go to the right. Due to lack of space, I'm going to put condition number 4 on the top. Condition number 4 says the following. If a column has a leading 1 for some row, then all entries above and below this leading 1 will be 0. Will be zeros. Now, I'd really like to have these 4 statements on the board while we look at matrices to see if they are in RREF form. So let me try to write it down on the very top, but obviously shorter notation. 0 rows on the bottom. That's number 1. Number 2. Leading ones go to the right as those rows go lower. That's number 2. Number 3. Oh, actually, I'm sorry. That was number 3. Number 2. First non-zero entry must be a 1. Number 4. Above and below leading ones must equal 0. Must be 0. So those are the 4 properties that must be true for a matrix to be in RREF form. And it's probably best, at least in my opinion, and most authors, that if you're going to test or check to see if a matrix is in RREF form, those are you should check in that order. Okay, you want to check in a different order? Fine. Not a big deal. But you must check those 4. You must verify those 4, and that's it. Don't verify 5 or 6 properties. Don't verify a different set of 4 properties. You have to verify those 4 properties. Suppose you have this matrix that has 5 columns and say 4 rows. 0, 0, 1, 2, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. Property 1 says the rows that have nothing but zeros must be on the bottom. Well, that's the only row that has zeros in this matrix, or nothing but zeros. And you know what? It's on the last row. It's on the last row. So property 1 has been verified. In each row, the first non-zero entry must be a 1. Well, when I look here, that's the first non-zero entry. And it's a 1. In the second row, it has a non-zero entry, a first non-zero entry, and it's a 1. In row 3, look at that. There's the first non-zero entry. Let me be very clear. That's 0, and that's 0, and that's 0, and that's 0, and that's not 0. And it's a 1. In the last row, there is no non-zero entry, or first non-zero entry. Okay, so condition 2 has been met. Condition 3 says that as you go down in the rows, the leading ones have to go to the right. They don't have to go just one column to the right. They have to go to the right. Well, here's a leading one. I went down, and the next leading one is to the right. Go down to the next row. The next leading one is to the right. That's good. That's good. Number 4, it says above and below the leading ones must be 0. Okay, well, like I said, that's a leading one. There's really no above, but everything below it is a 1. Here is another leading one. What's above and below it are zeros. Here is the next and the last leading one. What's above and below it is 0. For those of you who want to say, come on, but that's a 2. Fair enough. The thing is, there's no problem with that. In row 2, the first non-zero entry is a 1. And what's above and below are zeros. There's no problem. This matrix is absolutely in row-reduced echelon form. If you have, say, this matrix, is not in row-reduced echelon form. The reason is, here's a row of zeros, and it's not on the bottom. Again, I want to be very careful when I say it's not on the bottom. Here's a row of zeros. It's not the bottom row, but you know what? All of these are zeros, and they are on the bottom. Okay, we don't have a row that doesn't have all zeros either below it or in between it. The bottom 1 or 2 or 3 or 4 rows must be the ones that have the zeros. So that matrix that I didn't erase, the one in the bottom left, that matrix is not in RREF form because it failed property number 1. It failed property number 1. Okay. Now, what about this matrix? 1, 0, 0, 4, 0, 0, 3, 8, 0, 0, 0, 0. Well, condition 1 has been met. The row or rows of 0 are on the bottom. Good. But condition 2 has a problem. In row number 2, that's the first non-zero entry, but it's not a 1. to fail condition number 2. How about this matrix? Condition 1 has been met. It has a row with zeros, and it's on the bottom. For the record, it doesn't have to have a row with zeros. It can be 8, 0, 10, 0. Okay, now this matrix is not in RREF form because of condition number 3. Row 1 has this leading 1. Row 2 has that first non-zero entry, which is a 1. That's good. And this row, its first non-zero entry is a 1. That's all good. But condition 3 says the ones, as you go down the rows, the ones have to be going to the right. Well, here's a 1, as I said, and we went to the right. Good. But then we're not. We either went straight down or we go to the left. That's not good. Another problem with this matrix is the leading 1 in row 1 happens, well, let me just say it this way. Column 1 has a leading 1 for some row. Coincidentally, row 1. And what's below it is not all zeros. Row 2 has, column 3 also has a leading 1 for row 2. But what's above and below is not all zeros. What's above and below these leading ones have to be all zeros. And the ones have to be going to the right. If this 1 was over here, then it would have passed condition 3. The ones are going to the right as you go down. Another problem with this matrix is this row, the first non-zero entry, is not 1. These are all problems with that. Okay, this matrix here, 0, 1, 0, 0, 0, 0, 0, 1. Let's put another column. 0, 0, 0, 0, 1, and 0, 1, 0, 0, 0. Or, you know what, even if these ones here were zeros. And here is matrix I want. Oops. Okay. Suppose we have this matrix. It passes condition 1, and the number here is a 0. It passes condition 1. The bottom, we do a row of zeros, 2 rows, and they're on the bottom. Okay, so it passes condition 1. Condition 2 says the first non-zero entry must be a 1. That's true. In row 1, the first non-zero entry is a 1, and row 2, the first non-zero entry is a 1. But I don't want to talk about how it failed too. But it failed, you know what? Let me do it this way. Let's have a 0 here and a 1 here. So row 1 has a non-zero entry, first non-zero entry, and it's 1. So again, it passed criteria 1 because the row of zeros are on the bottom. It passed condition 2 because the first non-zero entry in each row is a 1. Oops, I want a 1 up here too. It passes condition number 3 because the leading ones
got it right. But it failed condition 4. Please, I put a 1 here. It failed condition number 4. Why? Because column 2
has a leading 1. Circle. Here was a leading 1 in the first row. Here's a leading 1 in the second row. 2 has a leading 1. But maybe what's below it, that leading 1 is 0, but certainly what's above it is not. That's not good. What's above and below the leading 1 must be 0. And again, I know I changed the matrix a few times, but there is a 1 above that leading 1 in column 2. Know the 4 rules, 4 properties of RREF form, for a matrix to be in RREF form. And equally as important, if not more important, you need to be able to look at a matrix and say, no, it violated one or more of the properties. The record, somebody asks you, is this matrix in RREF form? There's no need to verify all 4 of them, all 4 properties, if, for example, the second one failed. Because it doesn't matter if the third and fourth pass and the first pass, it's not in RREF form. They all 4 have to be satisfied. Okay. Now, the next thing is something called elementary row operations. We're going to do things to the rows. To be exact, we're going to do things to the rows of a matrix. I should have said matrix. We're going to do things to the row of the matrices to get them to be in RREF form. And what we're going to do are called elementary row operations. We're going to do operations on the rows of a matrix to get it to be in RREF form. Elementary row operations. And while I write these down, see if you see anything familiar with these operations. The first one is, let's just state, let A be a m by n matrix. So we can talk about row operations on A. You can interchange row R of A with row S of A. You can interchange any 2 rows. I bet you'll have some textbooks that say that R and S can't be the same. Well, what's the big deal? I'm not going to say they're wrong. I'm not even going to say I've ever seen that. I am going to say is, what's so terrible with interchanging row 3 with row 3? It's not going to, there really is no change. For example, even if you weren't allowed to interchange 2 rows, well, you can certainly interchange row 3 with row 3 because you really didn't do it. But okay, enough for that. You can interchange row R with row S of matrix A. You can multiply any row of A, call it row R. You can multiply row R of A by any real number C, but it has to be different from 0. You can't multiply a row by 0. And the third one is you can add a multiple of one row. You can add b times, and well, I guess b can be 0. We'll talk about that. You can add b times row R to row S. And row R and S are from A. Now, why can b be 0? Because 0 times row R will be a 0 row. And if you added it to row S, if you add zeros to each entry in row S, you get back row S. So we don't have to say b is not 0. Now, as a student, I really liked combining 2 and 3. It was my favorite step. So you can multiply a row by any number. And you can add a multiple of a different row to row R. So let's talk about, say, row R. Here's a matrix, and this is row R. You can you can do two things. You can multiply row R by any number. Say you multiplied it by C. So now you have CR. This is still matrix R. Row R. This is row R. It's C times row R. Okay? Now, you can take row S, and you can add b times row S. You can add b times row S to that matrix. So now, row R is now going to be b times row S plus C times row R. Now, to go from here to here, we performed 2 elementary row operations. From here to this matrix, we multiplied row R by a non-zero number. Elementary operation number 2. And then from here to here, we took row R, which is now C row R, and we added b times another matrix, another row, b times row S. Well, I like to just jump right to it. I'll call it condition 4. You can add a multiple of one row to a multiple of another row. Here's the multiple of one row, and I'm adding it to a multiple of another row. And that's what I call number 4. I put a star there because you don't need to have it. You don't need to have it. In mathematics, when it comes to a definition, you want to put as little as necessary. Yeah, of course you can do what I'm saying. But according to these operations, it's a 2-step process. Well, in my opinion, it comes up, or it should come up, so frequently that we'll actually denote it as one of the row operations. You can add, let me not say it so specifically. You can add a multiple of one row, add a multiple of one row to a, not just, or to another row, but to a multiple of another row. You can add a multiple of one row to a multiple of another row. And that's 2 and 3 combined. Now, I asked earlier, right before I wrote down these 3 or 4 elementary row operations, for you folks to see if it looks familiar. Well, imagine these rows were equations. Remember, we're trying to learn how to solve a system of equations. Instead of rows, just think equations. You can interchange equation R with equation S. I mean, the solution to 2x plus 3y equals 11 and 3x minus y equals 4. The solution to this has the same exact solution as this system of equations. All I did was interchange two equations, and I'll even put down a third one, which I didn't change its position. Whatever solutions this system of equation has, this one's going to have the same. I mean, just because I wrote down the equations in a different order doesn't matter. You know, this line and that line intersect right here. Intersects right here. But it doesn't matter which line I wrote down first. If I wrote down this line first and then this line, they still intersect at the same point. And we prove, well, let me first translate number 2 to equations. You can multiply an equation by any real number. Well, we actually, and you know, it won't change things. We actually proved that if you multiply an equation by a non-zero value, it doesn't change the points on that equation. I think we just proved it for a line. It doesn't change the points on the line. When you have line 1, it had the set of points. If you multiply the equation for line 1 by 17, this new equation has the exact same points. And we didn't prove number 3, but if you add b times equation R to equation S, it won't change. It'll still, the system of equations will still have the same solutions. If you add a multiple of one equation to another equation, the solutions will not change. The solutions will not change. That's very important. Okay, you should actually prove that one. Convince yourself that if you have any number of equations and you replace the ith equation by adding to the ith equation a multiple of the jth equation, the solutions will still be the same. It will still, the system of equations will still have the exact same solutions. Okay. I'm going to write down a matrix, and we want to get it into RREF form. 0, 0, 1, 3, 3, 2, 0, negative 4, 4, 4, 8, negative 12. Okay. The first thing I would like to do is get a non-zero entry in the top left position. I can either interchange row 1 and 2 or row 1 and 3. Now, maybe even before I do that, I can take the third row and divide each entry by 4 without creating fractions. 0, 0, 1, 3. Oh, notice I write the rule right by the row that I'm doing that rule to. You're going to be driving your teacher crazy if you just do these steps without writing down what rule you're doing, because if you make a mistake, the teacher's not going to, there's a good chance the instructor will not figure out what you meant to do. Okay, I mean, if you're going to add 3 times row 1 to 11 times row 2, and you don't write that down, and you don't make a mistake, that's going to be hard for your instructor to find out. If you make a mistake, it might be next to impossible for this person to figure it out. The other thing is you don't want to get the person, you don't want to make the person unhappy while they're grading your exam. You want to say, this is what I'm trying to do. If I made a mistake, well, you can easily catch it because I wrote down what I'm doing. I didn't write down anything by row 1 or row 2. Hence, I just copy it down. Rows 3. 1, 1, 2, negative 3. I like ones. Not because I want the non-zero entry, the first non-zero entry to be a 1. Okay, let's go over that. A lot of books, a lot of teachers are going to tell you, you have to get that leading entry to be 1 at the very beginning. Well, that might create fractions. For example, if this was row 1, that's the first non-zero entry. Even in row 2, it's the first non-zero entry. If I divide by 3, I'll create fractions. The first non-zero entry up until the very, very last step, it doesn't have to be a 1. If it's a 7, let it be a 7. The very last step will be to divide that row by 7, so the leading entry is not 7, but rather 1. I'd rather put this row in the first position. So I'm going to say row 1 and row 3 get interchanged. Row 1 interchange with row 3. And there's a reason I want to do that. It'll become clearer in examples that, say, have 4 equations, 4 rows. The reason is, okay, so here's my first row. Here is the first non-zero entry. Since it's a 1, I can get that number to become 0, more easily. Like if this were an 8, I can get that 8 to become 1 more easily versus having a 3 up here. For example, if this were a 3 and this really was an 8, I'd have to get these two numbers. This number 3, make believe it's a 3 in that position. To get this 3 to kill off the 8, I'd have to get them both to be 24 and then subtract. But being a 1 is very, very friendly. I don't have to do anything to the 8 to get the 1 to become an 8. Okay, but you have every right to say, what 8? So the first the leading entry is a 1. And it didn't create fractions. If I multiply this row by 3, this whole row by 3, I'll have a 3 here. And if I didn't do anything to row 2, the first entry will be a 3. So how about I do 3 times row 1, take away row 3. Take away row 2, excuse me. 3 times row 1 is 3 times 1, 3 times 1, 3 times 2, 3 times negative 3. And row 2 is 3, 2, 0, negative 4. And I am going to subtract because 3 and 3, when you subtract, you get 0. 3 minus 1, 6 minus 0, negative 9 minus a negative 4, it's negative 5. So the new matrix we get is 1, 1, 2, negative 3. Row 2 has been changed. Row 3 has not been changed. And notice, column 1 has a leading entry, and everything below it is 0. Wonderful. Now, what are these symbols that I keep writing? It means that this first matrix is row equivalent to the second matrix, which is row equivalent to the third matrix, which is row equivalent to the fourth matrix. And for the record, the first matrix is row equivalent to the third matrix. The first matrix is row equivalent to the fourth. The second and third are row equivalent. They're all row equivalent. Okay, let me get rid of my side work here. So erase the side work on the physical board and move on. So now we go on to row number 2. And we look for the first non-zero entry. And it happens to be a 1. In row 2, the first non-zero entry happens to be a 1. Okay, I couldn't care less what it was. Could have been an 11. I wouldn't want it to be a fraction. If you're starting off with row 2 having fractions, multiply through by a number that will kill off all the fractions. Okay, row 2, that's my first non-zero entry, and I want what's below it to be 0, and it is, and what's above it to be 0, which it isn't. So I need to change row 1. Well, if I just do row 1 minus row 2, that will kill it off. I mean, after all, 1 minus 1 is 0. Here is row 1. Here is row 2. I do subtraction, and I get that. So that's going to be the new row 1. 1, 0, negative 4, 2, 0, 1, 6, negative 5, and 0, 0, 1, 3. Let's move those over. Negative 5 and 3. Okay. Now, column 2 is fine. It has a leading, a first non-zero entry. What's above it and below it is fine. That is a 0. The first row has a first non-zero entry. What's above, which is nothing, and below are all zeros. Okay. Now we go on to column 3. Here, and notice my leading ones are going to the right. My leading ones are going to the right as we go down. They don't have to go one column to the right. Okay. So everything looks good except what's above and below this leading one has to be 0. That is, I have to get those to be 0. And luckily, that number is a 1. I'll take row 1, which has a negative 4 here, and I'll add 4 times row 3. And 4 row 3s do not affect the double zeros. That is, it won't affect that 0 right here. It won't affect the 1 either, but I didn't care about that. If it affected the 1 and it became 7, at the end, if I still had a 7, I'll divide by 7. But I don't want to lose the 1. That's the 6. I'll keep row 2 the way it is, but I'll take away 6 row 3s. And let me do that work somewhere and then write down the matrix. I'm pretty sure this will be the last step. So row 1 is 1, 0, negative 4, 2. Here is row 1. I'm going to multiply row 3 by 4. 4 times 0, 4 times 0, 4 times 1, 4 times 3. And if I add these, I get 1, 0, 0, 14. So row 1 becomes 1, 0, 0, 14. Hopefully I'm not making some silly arithmetic error, but it's the concept. It's not arithmetic errors. You can be quite brilliant in linear algebra. You can be an algebraist, but not be able to reduce a matrix. The concept that matters. Row 2 becomes row 2 minus 6 times row 3. Row 3 is 0, 0, 1, 3. It's right here. 6 times 0, 6 times 0, 6 times 1, 6 times 3. And if you subtract, you get the 0 you want. And negative 5 minus 18 is negative 33. 0, 1, 0, negative 33. And the last row, we're not doing anything to it. Now, what you should do at this point is to get there in each row that has a non-zero, a leading entry, get them to be 1. But fortunately for us, they already are 1s. Now, minus some silly error, this is your answer. And my concern is this isn't what I got when I did it myself. So I'll give a quick look from the first matrix to the second. I do not see a mistake.
The third matrix, all I did was interchange 2 rows, kept the second one the same. So matrix 3, I don't see a problem. Matrix 4, I change the second row. 3 times row 1.
Take away row 2. Okay, negative 1. Okay, I don't see a problem with matrix 4. Let's take a look at matrix 5. I just 4 to 5, as it says. For row 1, I replace it with row 1 minus row 2, which means the second and third row should not have changed, and they did it. And the first row should be 1, 0, negative 4, 2. It's exactly what I have for matrix 5. So matrix 5 is okay. On to matrix 6. The third row I did not change. 1, 0, 0, 14. First row of the last matrix is right. The second one, 0, 1, 0, 8, negative 5 minus 18 would have been negative 23. Okay, other than that, there it is. I don't see anything else wrong. So this matrix did satisfy all 4 criteria. If it has a row of zeros, they're on the bottom. There's no counterexample to that. All the rows are zeros. The second condition was the first non-zero entry in each row had to be 0. Well, I bought first non-zero entries, yes. And they're all 1s. The first non-zero entries have to, I might have just said zeros, I'm sorry. They have to be 1s. And the leading ones, as you go down, they have to go to the right. Not one column to the right. They can go 4 and 5 columns to the right, but they have to go to the right. And they do. And above and below each leading each leading ones are zeros. In column 1, that's my leading 1. What's below it is 0. There is no above. In column number 2, my leading 1 is right here in the middle. What's above and below are zeros. In column 3, here is my leading 1. What's above are zeros. What about column 4? It did not have a leading entry. So don't worry about above and below. This matrix is now in reduced row echelon form. Let's try one more. You guys need to try 43 more. Possibly. And you need to be able to do this. Now, if you're doing everything right, that is, what you're writing on the side of the matrices are the correct steps, but maybe you make a silly arithmetic mistake, well, be more careful. Be more careful. But if you don't know what to write on the sides, that's another issue. Okay? Personally, I'd rather know what to write on the sides and make silly arithmetic mistakes than to never ever make arithmetic mistakes, but not to know what to write on the side. Because if you don't know what to write on the side, that's much, much more serious than once in a while you saying 7 plus 2 is 11. You know what 7 plus 2 is. It's 9. If you say it's 11, it's funny. It's not sad. You have to know what to write on the sides. Let us reduce this matrix. Since there's a 1 in that 1, 1 position, that's wonderful. Otherwise, I might interchange row 1 and row 2. Here is my first non-zero entry in row 1. I want to get what's below it to be 0. I want to get this 1 to be 0. I'll do row 1 minus row 2 minus row 1. Personally, I decide on by looking to see which will give me more positive numbers. Now that's a 2. If I double row 1, it puts a 2 here. And if I do nothing to row 2, row 3, it puts the 2 there. 2 and 2, subtract, get 0. So row 1 is not changing. 1, 2, 4, 2. Row 2 becomes row 1 minus row 2. Well, row 1 is this set of numbers. Row 2 is this set of numbers. When you subtract, you get 0, 3, 2, negative 1. Now, please, I don't mind that you get 0 when you say 1 minus 1. I wouldn't even mind if when you subtract those, they're not the same. Okay, scratch that. 0, 3, 2, negative 1. What I'm saying is, if you're subtracting, I don't mind if you say this is 0. I don't even mind that much if you say that's 0. Okay? What I do mind is you're starting with 1 and you're subtracting in both cases. You're subtracting in both cases, but you're subtracting different numbers. How can you start at 1, take away different numbers, and get the same answers? That you should catch. That you should catch. I hate having check marks when it's wrong. 1 minus a negative 1 is 2. Becomes 1 plus 1. But if you have 7 and you take away 3 and you say that's 4, and the very, very next problem is this, me personally, if I didn't know what it was, I would say, well, I know one thing. It's not 4. Because if you start at 7 and you take away 3, you get 4. If you take away a number other than 3, you won't get 4. Okay, catch that mistake. Okay, side work. You don't have to erase it on your scrap paper. But I need more space. Now we need to find out what the new row number 3 is going to be. It's going to be twice row 1. Take away row 3. Twice row 1. I'm going to multiply each of these numbers by 2. 2 times 1, 2 times 2, 2 times 4, 2 times 2. Rows 3, 2, 1, 3, 2. Subtract. Why? Because I want this to be 0. And whatever I get for the other numbers, I have to live with. 0, 3, 5, and 2. Okay, let's get rid of our side work. Notice that column 1 is complete. It has a leading entry, coincidentally for row 1. Column 1 has a leading entry, and what's below it, they're all zeros. So now we go on to row 2. The first non-zero entry is 3. In theory, I can switch these two, but that's also with 3. Gotta live with this 3. I want to get this to be a 0, and I want to get that to be a 0. And I'm going to use this row. Usually, you should use the row that has the leading entry that you're working with. We're dealing with row 2, and that's the leading entry. Well, if I just do row 3 minus row 2, I'll be doing 3 minus 3. And 5 is bigger than 2, and 2 is bigger than negative 1. So I'll do row 3 minus row 2 versus row 2 minus row 3. Now, when it comes to row 1, due to lack of space, I'll write down what I'm doing above. I have a 2 and a 3. The least common multiple of 2 and 3 is 6. So I need to triple row 1. That'll put a 6 here. I need to double row 2. That'll put a 6 there. And I need to subtract. I didn't write any statement by row 2. So I just copy it down. What is 3 times row 1, and what is 2 times row 2? 3 times row 1. I literally multiply each entry by 3. 3 times 1 is 3. 3 times 2. 3 times 3 is 9. Well, yes it is, but that's not a 3. It's a 4. 3 times 4 is 12, and 3 times 2 is 6. 1, 2, 4, 2. Okay, that's 3 times row 1. 2 times row 2, 2 times 0, 2 times 3, 2 times 2, 2 times negative 1. And I subtract 3 minus 0, 6 minus 0, 6 minus 6 is 0 like I wanted. 12 minus 4. 6 minus negative 2 is 8. Okay, so That is the new row 1. 3, 0, 8, 8. And I'm not going to cry that I lost my 1. It's not a big deal at all. Okay, now, row 3, take away row 2. Row 3 is 3, 0, 5, 2. And row 2 is 0, 3, 2, negative 1. And then I subtract. 0, 3 minus 3, 5 minus 2, 2 minus a negative 1. And I get what I get. 0, 0, 3, 3. Notice, second row, that's my leading entry. What's above and below is 0. Wonderful. So now we look at row number 3, and we look to see if there's a leading entry, a non-zero entry. And it'd be so nice if there wasn't, but there is. It's just 3. So let's talk about how we're going to get above and below that leading entry to be zeros. Or maybe we want to change that leading entry. Since the leading entry is 3 and not a 1, that's not the greatest news, because I have to use a 3 and an 8 to kill off the 8. And the LCM of 3 and 8, the first common multiple, is 24. I'd have to multiply row 1 by 3 and row 3 by 8 to get 24. And then the LCM of 3 and 2 is 6. Have to multiply row 2 by 3, row 3 by 2. Be headed. But you know what? All of these 3 numbers, let me try that again. All of these 4 numbers are on the 3 times table. 3 times 0 is 0. I can divide every entry in row 3 by 3. So I'm not touching the first row. I'm not touching the second row. And I'm dividing row 3 by 3. 0 divided by 3 is 0. 0 divided by 3 is 0. 3 divided by 3 is 1. 3 divided by 3 is 1. Now, the LCM of 1 and 8 is 8. I'll just keep row 1 the same. That puts an 8 there. I'll multiply rows 3 by 8. That puts an 8 there. And I'll subtract. Row 2 has a 2 there. If I multiply row 3 by 2, it'll have a 2 there. And I subtract. And once I do that, it should take care of column 3. And notice the way I'm doing it, I'm not affecting column 1 and 2. At least not, well, not where the leading, not affecting column 1 or 2. Possibly I'm changing the leading entries to something else, but I'm not getting rid of the zeros. The zeros have to stay. Okay, the zeros have to stay. If you look at the top right matrix, I have 1, 0, 0. And if you look at the next 2 matrices, I have 3, 0, 0. I can get the 1 back easily, but not the zeros. The zeros, we work hard to get. Don't give up the zeros. Okay. Row 1, 8 times row 3. Row 1 is 3, 0, 8, 8. And 8 times row 3 is 0, 0, 8, 8. And if you subtract, you get 3, 0, 0, 0. Okay, wonderful. 3 and then 4 zeros. And for the record, we're not changing the last row. But we are changing the middle row. We're doing row 2 minus 2 row 3s. How do I know that? I read it off. Right by row 2, I read off what we're doing. Write it down. Now think about it. Maybe a teacher marks it wrong. And who knows? Maybe they're not right for marking it wrong. Maybe you did it right. You think you're going to remember what you did? You think you're going to remember that you did row 2 minus 2 row 3s? Maybe not. But if you write it down, you don't have to remember it. Okay, so there's a motivation to have you write it down. If you don't care about your teacher losing his or her mind sorting through your arithmetic, think about the fact that maybe your teacher made a mistake and you need to know whether or not a mistake was made. 3 minus 0, 2 minus 2, negative 1 minus 2 is negative 3. Okay, 0, 3, 0, negative 3. Other than having ones for the leading entries, this matrix satisfies all the other conditions for our REF form. Row 1, that's the 3 is their non-zero entry. In row 2, that's the first non-zero entry. In row 3, this is a non-zero entry. The row of zeros, there are none. The leading entries keep going to the right. And in column 1 has a leading entry, and everything else is 0 but the leading entry. Column 2 has a leading entry, and everything else in that column is 0. Column 3 has a leading entry, and everything else in that column is 0. And column 4 does not have a leading entry for any row. So now I'll get the ones. I'll take row 1, I'll divide it by 3. I'll take row 2, and I'll divide it by 3. Row 3 already has a 1 there. So we are done now. 3 divided by 3, 0 divided by 3, 0 divided by 3, and 0. 0 divided by 3, 3 divided by 3, 0 divided by 3, and negative 3 divided by 3. And the last row, we don't do anything to. This matrix is an RRF form. Reduced row 1 form. It's a lot of steps, absolutely. But you need to do this. You must do this. Now at the beginning, I commented that we're going to learn in this section how to use matrices to solve system of equations. In fact, we use augmented matrices. The process that you use to solve a system of equations is called Gauss-Jordan method, or Gauss-Jordan reduction. We're going to solve the next system of equations using matrices and the technique of Gauss-Jordan reduction. Solve the following system of equations. Of course, for us, it's always linear equations using Gauss-Jordan reduction. That just means to get the matrix in RREF form. Now, what comes to the right of the augmented line, or though, you use that entry when you make changes in the rows. Don't worry about getting that that column in RREF form. In other words, if in the end, or if at some point you had something like this. Now this matrix, forget, make believe just that matrix. That matrix is in RREF form. Okay? Now, if the last column was this, row 3, there's my first non-zero entry. It's a 1, wonderful. I have to get what's above and below 0. No. You just reduce this portion. Whatever is here is fine. It's fine. Don't reduce the last column, the one to the right of the line. That is why we put the line. Okay, don't worry about the last column. In fact, from now on, when I say the last column, I don't even mean that column. I mean the last column to the left of that augmented line. So suppose you have x plus 2y plus z, and, 2x minus y plus 2z, and 3x minus y plus 2z, and let's see, 3, 6, and 7. Suppose we have this. Okay. The first thing is we need more space, okay? We need more space. So I'm going to write it down without saying the steps, stating the problem. That is, solve the following system of equations using Gauss-Jordan reduction. Just going to write down the equation. I'm pretty sure that I will remember it. This equals 3, 2x minus y plus 2z, that was 6, and 3x minus y plus 2z equals 7. To be honest, I didn't remember it. I didn't erase my blackboard all that well, and I was able to read it off. Write the augmented matrix. Just remember that there's a 1 here, and a 1 here, and there, and there. So the numbers in front of x's are 1, 2, and 3. And in front of y's are those numbers. Always include the signs. In front of z's are those numbers. And the right-hand side is 3, 6, 7. Now, in this case, if that first row was in another position, I would get it in row 1. Because the first non-zero entry is 1. And I could use the 1 fairly easily to kill off the 2 and the 3. If I had the 3 on the top, that would be a nightmare. Unless I switched row 1 and row 3. All right. To get rid of the 2, if I kept row 2 the same, I'll have a 2 in that position. And if I double row 1, I'll have a 2 in the first column position. I'll subtract. If I leave row 3 alone, I'll have a 3 here. If I tripled row 1, I'll have a 3 in that top position. And then I subtract. Okay, so on the side, I'll do this work, except row 1 did not change. I know it didn't change. I didn't write anything by it. row 2, I'm going to take away 2 row 1s. Well, row 2 is, so if you write something here, it corresponds to this matrix. Row 2 is 2, negative 1, 2, 6, and twice row 1 is 2, 4, 2, 6. And I subtract. I get 0, negative 5, 0, 0. Probably would have been better if I did 2 row 1s minus row 2. That means all these signs would be wrong or different. That is, it would be 0, 5, 0, 0. When you negate 0, you still get 0. Okay, for the third row, row 3, and I'm going to take away 3 row 1s. Row 3 are these numbers. Notice I am including the numbers to the right of the line. 3 row 1s are 3, 6, 3, 9. And if I subtract, I get my 0. Negative 7, negative 1, negative 2. Okay, 0, negative 7, negative 1, negative 2. I just hate all these negatives. I'm going to do negative 1 times row 2 and negative 1 times row 3. To save a little space, I'm just going to do it right here. This will become positive 5, positive 7, positive 1, and positive 2. All the other numbers were zeros, and when you change the sign of 0, first let me point out when you multiply by negative 1, all you do is change the sign of the number. And when you change the signs of zeros, they stay 0. It's magic. I tell you, mathematics is magic. If you multiply 0 by negative 1, it stays 0. Only more numbers behave like that. Like you multiply a number by 7, it doesn't change. Then everyone would be experts on the 7 table. 7 times 50, I know what that is. It's 50. 7 times 5, it's 5. But unfortunately, it's not like that. Okay. First column is done. Here's my leading entry. What's below it is 0. Go to row 2. The 5 is my leading entry. I need to get what's above it and below it to be 0. To kill off the 2, well, the first common multiple of 2 and 5 is 10. Got to multiply 2 by 5 and 5 by 2. So I multiply row 1 by 5 and I multiply row 2 by 2. That will put a 10 in that second column position. Subtract the 10s, you're done. You get 0. The LCM of 5 and 7, 35. If this is their leading entry you're working on, you have to deal with that row. I want to use that row to kill off the 7. Well, if I multiply row 3 by 5, I'll get a 7 there. And if I multiply row 2 by 7, if I multiply row 3 by 7, I'll get a 35 there. And if I multiply row 2 by 7, I'll get a 35. Subtract the 35s, you have 0. Oops. Okay, everything I said is absolutely correct. And look at all the work I need to do. I need to multiply for row 1, I need to multiply row 1 by 5, row 2 by 2. To kill off the 7 in row 3, I have to multiply row 1 by 3 and row 2 by 7. It's a nightmare. Okay, I could say that I planned that, quote, mistake that I made. But That's kind of complicated doing all that. But if I simply divide row 2 by 5, I just have a nice 1 there. If I divide row 2 by 5, I just have a 1. Because all of the numbers in row 2 are divisible by 5. Now you may say, and I didn't point this out earlier, first let's write row 2. You may say, well, you only said earlier one of the elementary row operations were you can multiply any row by any non-zero number. You never said divide. Well, this is true. We're really multiplying row 2 by a fifth. But it's the same as dividing by 5. Now, I will admit, if your teacher is really, really picky, he or she can say, no, I'm going to take a point off for that. You can't divide. That's not one of the row operations. In my opinion, they should get over that. That's being a little bit picky. And trust me, I am very picky when it comes to grading. But I would not mark that wrong. But if your teacher's like that, no big deal. Write 1/5 R2. Write 1/5 R2. I'm not changing row 1. I am changing row 2. And I'm not changing row 3. Other than those signs. I'm multiplying by -1. Okay. Second row, first non-zero entry. So 1. 1 is a wonderful number because I can get 1 to be any number I want it to be. Just multiply by that number. If you want 1 to become 7, multiply by 7. That is, the LCM of 1 and any other integer is that integer. The LCM of 1, and x, but x is an integer, is x. That is, you don't have to do anything to x to get it to be x. And what do you do to 1 to get it to be x? You multiply by x. If I keep row 1 the same, I have a 2 there. If I double row 2, I'll have a 2 there. Subtract. If I keep row 3 the same, I'll have a 7 there. If I multiply row 2 by 7, I'll have a 7 there. Subtract. It's a lot easier when we realize we can get that 5 to become a 1. The price you pay for not seeing that is a lot more calculations. You'd have to multiply row 1 all across by some number. I think it was 5. You'd have to multiply row 3. To change row 3, you would have had to multiply row 3 by 5. It was 5 row 3s minus 7 row 2s. To change row 1, it was 5 times row 1 minus 2 times row 2. All right, so let us do this arithmetic. The second row did not change. Let's put this line in the middle. Row 1 is 12, 13. 2 times row 2. Well, that's easy. They're all zeros except the 1 in the second position gets multiplied by 2. If you subtract, you get 10, 13. 10, 1, 3. Now, if you do row 3 and you take away 7 row 2s, row 3 is 0, 7, 1, 2. 7 times row 2 will be 0, 7, 0, 0. You subtract, you get 0, 0, 1, 2. 0, 0, 1, 2. All right. Unfortunately, this last matrix is not in RREF form. Again, do not look to the right of that line. Look to the left of the line and try to figure out why I just made that statement. Why I feel it's not in RREF form. The reason is, in row 3, here's my leading entry. What's above it is not all 0. What's right above it is 0, but the whole column has to be 0. Well, 1 minus 1 is 0. These are, this entry and this entry are 1. I'll just do row 1 minus row 3. Here is row 1. Here is row 3. If I subtract, I get 1, 0, 1, 1. 1, 0, 0, excuse me, 1. Okay, so the first row becomes 1, 0, 0, 1. The second row, I didn't do anything to. And the third row is this. Okay. This matrix is in RREF form. Okay, we just did Gauss-Jordan reduction. Why is it not called RREF reduction? The only thing I can think of is because of the right column, the augmented matrix. Okay. But the problem said to solve the system of equations. I don't see any answer. I don't see what x equals. I don't see what y equals. I don't see what z equals. Well, my response is you have to look a bit more closely. That first line says 1x plus 0 y's plus 0 z's. That line means equals 1. Well, 0 y is 0. 0 z's is 0. 1x is x. X plus 0 is x. X equals 1. 1x equals 1. The second row, it says that 0x's, 1y plus 0z's equals 0. 0x's plus 1y plus 0z's equals 0. But 0x's are 0. Plus 1y is 1. 0z's are 0. And 0 is 0. But 0 plus x, 0 plus y plus 0 is just y. So y equals 0. And I guess I'll go to the far left to solve this one. 0, 0, 1, 2. 0 x's plus 0 y's plus 1z equals 2. 0 x's plus 0 y's plus 1z equals 2. 0 x's plus 0 y's plus 1z equal to 2. That's 0 plus that's 0 plus 1z is z equals 2. But 0 plus 0 plus z is 2. Z equals 2. We'll come up here, z equals 2. Why am I coming back there? Because everything I'm putting a box around, that was just side work. You should be able to read it off more quickly. In the second row, and I'm only talking about to the left of this line, there's only one non-zero entry. That's a 1. First column are x's, second columns are y's, third columns are z's. Remember, the first column of numbers, 1, 2, and 3, they came from their x's. The second column of numbers, 2, -1, 1, they came from the numbers in front of the y. the 1, 2, 2, the 1, 2, 2, they came from the numbers in front of z. And the numbers after the equal sign, oh, that came after the line. Okay. 1z is equal to 2. 1y equals 0. 1x equals 1. Exactly what I said. Exactly what I said. X is 0. Y is, X is 1. Y is 0. Z is the number 2. Okay, we will try another problem like this. You need to solve these for a while before you start getting good at it. Nobody, especially me, nobody starts off being really, really good at these. You need to solve 10, 15, maybe 20, who knows. Eventually, you'll start doing really well with these. This is a must for you to pass your linear algebra class. If you can't solve a system of equations, the next problem is x plus y plus 2z, x plus y plus 2z minus 5w, 2x plus 5y minus z minus 9w, 2x plus y minus z plus 3w, x minus 3y plus 2z plus 7w, and let's see, 3, negative 3, negative 11, and negative 5. First thing we need to do is translate this to an augmented matrix. The numbers in front of x's from top to bottom are 1, 2, 2, and 1. 1, 2, 2, and 1. The numbers in front of y are 1, 5, another 1, and a negative 3. 1, 5, 1, negative 3. The numbers in front of these are 2, the understood negative 1, again negative 1, and 2. And the numbers in front of w are negative 5, negative 9, 3, and 7. And the right-hand side numbers are 3, negative 3, negative 11, negative 5. The right-hand numbers are the numbers that come after the equal sign. And that at the top right, that's the matrix we want to use Gauss-Jordan reduction on. We want to get this matrix to be in RREF form. I'm going to try to give myself a little bit more space on the right. That way I'll be able to write down the procedures that I want to do. Negative 11 and negative 5. The first row, first position is a 1. If it was a 2, maybe I would interchange rows so I get a 1 there. If I want to kill off the 2. Between 2 and 1, the first common multiple is 2. So I'll leave row 2 the way it is. It has a 2 there. But I'll double row 1. And then both 2's I subtract. Same thing with row 3. I'll leave row 3 the same, but I'll take away 2 row 1's. When it comes to getting rid of the 1 in row 4, I'll do row 1 minus row 4. When it comes to subtraction, you can always do it the other way. Instead of a minus b, you can write b minus a, because you'll still get a 0. Row 1, no change. Row 2 is going to be whatever row 2 is minus 2 row 1's. Row 2 is 2, 5, negative 1, negative 9. And twice row 1 is 2, 2, 4, negative 10, and 6. And that should also be negative 3. Some people put a line there. It's not wrong. 2 minus 2, 5 minus 2, negative 1 minus 4, negative 9 minus negative 10, negative 3 minus 6. I get 0, 3, negative 5, 1, negative 9. And also a 3. Let me move the 1 over just a little bit. Okay. The third row is row 3 and then take away 2 row 1s. Well, row 3 is just row 3. And 2 row 1s are 2, 2, 4, negative 10, and 6. And when you subtract, you get negative 1, negative 5, negative 2, 17, and negative 11. Since I got mostly negatives, I'll multiply by negative 1. The 17 becomes negative 17. Just something quick that we can do. 1, 5, 2, negative 17, and 11. Okay, but we have to do row 4. Maybe I can do that on the spot. 1 minus 1 is 0. 1 take away negative 3 is 4. 2 minus 2 is 0. Negative 5 minus 7 is negative 12. And 3 take away negative 5 is 8. Okay. I notice row 4, all the entries are multiples of 4. So I'll divide by 4. Now, you should definitely make another matrix, and the first three rows will be the same, and the fourth row you will divide by 4. Me, to save a little space, I'm going to divide by 4 right on the spot. 0 divided by 4 is 4. 4 divided by 4 is going to be 1. Oh, okay. 4 divided by 4 is going to be 1. 0 divided by 4 is still 4. But negative 12 divided by 4 will be negative 3. And 8 divided by 4 will be good old 2. And I don't have to say I'm dividing by 4 anymore because I just did. Okay, now, something obviously went wrong because I have a 1 there. And that's in rows 3. Let's do it again. Rows 3 take away 2 row 1s. Rows 3 is 2, 1, negative 1, 3. And 2 row 1s will be 2, 2, 4, negative 10, 6, and this is negative 11. And if I subtract, I get my 0. And I get negative 1, negative 5, 13, and negative 17. So, to be honest, I'm not sure what happened there, but I had a few mistakes. Possibly I copied down one of the rows incorrectly. Okay. 0, negative 1, negative 5, 13, and negative 17. Okay. actually worked this one out, and all of a sudden it looks like I have incorrect numbers. Oh, okay. Okay, so everything is fine. What I would do here, and so now row 1 has that leading entry, and everything else in that column, namely column 1, is good. Now I go to column 2. I see a lot of 1s, but I see is 3 in row 2 for their leading entry. I don't want that. I'm going to switch, say, these 2 rows. Okay. Row 2 gets switched with row 3. And I'm also going to multiply row 3 by negative 1. So the first row does not change. The second row becomes row 3, is row 3 multiplied by negative 1. The third row becomes row 2. And the last row stays the same. Okay. So now row 2 has that leading entry. I want to get what's above it and below it to be zeros. And most of what's above and below, at least in 2 of the 3 cases, is the number 1. And the number 3 is easy to kill off because the leading entry is 1. The leading entry is 1. That's very, very friendly. Can't be any friendlier than that. Okay. So what I'm going to do is, for row 1, since this and that are both 1, I'll just do row 1 minus row 2. For the last row, I'll do the same thing. Row 4 minus row 2. But for the third row, since I have a 3 there, I'll keep the 3 the same, but I'll triple row 2. And then I subtract. So here is row 1. Here is row 2. And I'm supposed to subtract. I get 1, 0, negative 3, 8, negative 14. That is row 1. 1, 0, negative 3, 8, and negative 14. Row 2 does not get changed. And row 3 does get changed. Row 3 is row 3 minus 3 row 2s. This is row 3, and 3 row 2s, 3 zeros, 3 1s, 3 5s, 3 13s, and 3 17s. And you subtract, you get 0, 0, negative 20, 40, and negative 60. Now, there's no problem dividing by negative 20 right away. 0 divided by negative 20 are zeros. Negative 20 divided by negative 20 is 1. This divided by negative 20 is negative 2. And this divided by negative 20 is 3. So that's the new row 3. 0, 0, 1, negative 2, 3. And let me erase this so I can calculate what the new row 4 should be. It's going to be row 4 minus row 2. So it just takes forever to do this, fair enough, but you have to do it. You have to do this. Row 4 right here minus row 2. 0, 1, 5, negative 13, 17. When you subtract, you get this. And I can divide this by negative 5. 0 divided, because I want a 1 here, eventually. 0 divided by negative 5, 0 divided by negative 5, 1 divided by negative 5, yeah, negative 5 divided by negative 5, 10 divided by negative 5, and negative 15 divided by negative 5. I get 0, 1, 0, 0, 1, negative 2, 3. Okay. Column 2 has a leading entry, and everything else is 0. I go to row 3. Here's my leading entry. I want what's above and below to be the number 0. Now, remember that we talked about how two lines could meet in infinitely many points. Two planes, which is three-dimensional, could meet it, have infinitely many points of intersection. Well, we're in 4 dimensions, whatever that is. So we can have, once again, infinitely many solutions. Negative 3 and 1. If I keep row 1 the same, I'll have negative 3. If I triple row 3, I'll have 3. If you have negative 3 and 3, and you want 0, just add. 5 and 1. If I keep row 2 the same, I'll have a 5 right here. If I multiply row 3 by 5, I'll have a 5 there, where the 1 is. Subtract, you get 0. And I hope that you see that row 3 and row 4 are the same. So you just subtract, and you'll get all zeros. Okay. So let's see. The third row, we're not changing. The fourth row is exactly like the third row. So when you subtract, you'll get all zeros. And I'll do my side work at the top right. I'll get rid of this. I'll do my side work at the top right. I will attempt to do my side work at the top right. There we go. Okay. So for row 1, I need to do row 1 plus 3 rows 3s. So here is row 1. And here is 3 rows 3s, 0, 0, 3, negative 6, 9. And if I add them, I get my 0 here. 1, 0, 2, negative 5. Okay, that's row 1. 1, 0, 0, 2, negative 5. Now I want to do row 2 minus 5 rows 3s. So let's make some more space. Let's do it. Row 2 is 0, 1, 5, negative 13, 17, and 5 rows 3s are 0, 0, 5, negative 10, 15. And to kill off those 2 5s, subtract. You get this. 0, 1, 0, negative 3, 2. Couple of comments. if our bottom row is 0, except for the number to the right, say you have an 8, well, that creates a problem, because 0x's plus 0y's plus 0z's plus 0w's should equal 0, not 8, not negative 11, not 15. If you reduced and you got this with an 8 on the bottom right, you would say no solution. There is no solution. But it equals 0. There is no contradiction there. 0x's plus 0y's plus 0z's plus 0w's equals 0. The bottom line is true. Okay, now need to make a bit more space because this might get complicated for some of you. This problem is going to have an infinite number of solutions. Now, the first thing we need to do is to figure out how we could know it's going to have an infinite number of solutions. It's going to have an infinite number of solutions because there is what is called a free variable. There is a free variable. Let's identify the leading entries. Here's my leading 1 for row 1. There it is for row 2. There it is for row 3. Row 4 did not have any. Okay. That means, so the columns are X, Y, Z, and W. Column 1, just look at column 1. It had a leading 1. Column 2, if you look just straight down column 2, it has a leading 1. Column 3 had a leading 1. But column 4 did not have a leading 1. Column 4, that is variable W, is said to be an open variable. That is, W can be any number we want. The first equation that comes from 1, 0, 0 to negative 5. This means X plus no Y's plus no Z's, I'm going to stop writing that, plus 2 W's is equal to negative 5. That's one equation. The second row, 0, 1, 0, negative 3, 2. 0 X's, 1 Y, plus 0 Z's, minus 3 W's is 2. That's the second equation. The third line, 0, 0, 1, negative 2, 3. 0 X's plus 0 Y's plus 1 Z minus 2 W's is 3. Solving for X, Y, and Z, bring the 2W over. X is equal to negative 5 minus 2W. Y is equal to 2 plus 3W. Just bring the negative 3W over as plus 3W. The last line says that Z is 3 plus 2W. Okay. We're still not done. We're still not done. Just one more comment, one more line, and we can write down the answer. This problem, it has lots and lots of answers. Infinite number. I'm going to let W is equal to R. Any real number. And then we'll solve for X, Y, and Z in terms of W. X is equal to negative 5 minus 2W. But W is R. Y is equal to 2 plus 3W. But W is R. And Z is equal to 3 plus 2r. This is your answer. Why? So what does it mean that's the answer? Well, you can pick any number for r. You can pick any number for w or r. Okay, so I wrote down the solution. The problem is done. Anything I write now is just so you understand it better. That bottom right corner, that is the solution. But you can argue, but it doesn't say what x equals. You know, it doesn't say x is 11 or so on. You can pick any number for r. If r is equal to 0, then x will be negative 5 minus 2 zeros, which is negative 5. Y is 2 plus 3 times 0. 3 times 0 is 0. This is 0. 2 plus 0 is 2. Z would be 3 plus 2 zeros. And W is R, which is 0. Here is what's called a particular solution. When x is negative 5, y is 2, z is 3, w is 0, it will satisfy all 4 equations. What about if what if r is 1? Then x is, this will be 2 times 1 or 2. Negative 5 minus 2, negative 7. 3 times 1 is 3. 2 plus 3 is 5. 2 times 1 is 2. 3 plus 2 is 5. And w is r, which is 1. Here is another solution. If x is negative 7, y is 5, z is 5, and w is negative 1, this top equation would work. That is, all 4 equations, if you plug in negative 7, let's just look at one example. The first equation is x plus y plus 2z minus 5w is 3. If I use those answers, x is negative 5, add on y, which is 2, add on 2 z's, which is 6, take away 5 w's, and 5 times 0 is 0. Negative 5 plus 2 is negative 3. Negative 3 plus 6 is 3. Take away 0, yeah, we got 3. And these numbers, negative 5, 2, 3, and 0, they will work in all 4 equations. Let us show that the second solution also will work in at least one of their equations. Say the last equation. X minus 3y's plus 2z's plus 7w should equal to negative 5. Even if I use those numbers for x, y, z, and w. X is negative 7 minus 3 5's. 3 times 5 is 15. Plus 2 z's are 10. Plus w is 1. 7 ones are 7. This gives you negative 15. Negative 22. You take away 7, and then you take away 15 more. You took away 22. And you add back 10. You have $22 in your hand that you just took out of the bank, and you give the teller back $10. Well, you have $12 in your hand. And then you add 7 more. Negative 12 plus 7, it's negative 5. But of course, you have to use these 4 numbers if you wanted to check. You have to use them in all 4 equations, and it would work. This is a solution because if you plug in negative 5 for x, 2 for y, 3 for z, 0 for w, this left-hand side will equal 3. this left-hand side will equal -3. Same thing with the third and fourth equation. Using these numbers for x, y, z, and w, the third equation will be -11, and the fourth one will be -5. Same exact story for these four numbers. And you can pick other numbers for r, one number at a time. You can let r be 10. So w will be 10, x would be -25, y would be 32, and 23 for z. This is when r is 10. Okay, so you have yet another solution. And of course, you can be here all day writing down solutions. You can let r equal pi. You can let r equals -2/3. You can let r equal -8. You can let r be 4. You can let r be 0.021. Any real number. R can be any real number. And when you pick different numbers for r, you get different solutions. There is an open variable. Sometimes you can have two open variables. Okay, we'll do that rather quickly. I'll give you the final matrix. I'll give you the final matrix, and it will have two open variables. So since I don't know the letters of the variables yet, they'll probably be z and w, you can then say that one of the variables is r, any real number, and the other open variable is s. Okay, so suppose you were given a system of equations, you wrote down the augmented matrix, and you reduced the augmented matrix. And you came up with the following. 1, 0, 0, 0, 0, 0, 1, 0, and then two rows of zeros. Or even one row of zeros. It wouldn't matter. And the right-hand side was 7, 2. Now, if I had -3 and 0, you should say there's no solution, because once these are all zeros, 0 times x plus 0 times y plus 0 times z plus 0 times w couldn't possibly equal -3. Okay, so I'm going to make, so there'll be no solution. There will be no solutions. These four-dimensional objects, they don't intersect. There will be no solutions. Let's write down the ones, sorry, the zeros together. All right. This matrix is in reduced row echelon form. And I say the matrix, I just mean to the left of the augmented line. Okay. Column X has a leading 1. There it is. And that's also a leading 1. Those are the two leading ones. Column Y does not have a leading 1. Column Z does, and W does not. So Y and W are open variables. Y, so X, Y, Z, and W. Y is R. Any real number. And W is S. Any real number. Now, the first line says that, well, let's make it even more interesting. I kind of made it very boring. Sorry about that. I made it a little bit boring. What if we had this? What if we had that? That's the 4 over here. What if we had this? This with a 4 here. This matrix is still in RREF form. The first equation says that x plus 2y plus 3z's is 7. But plus 3 w's. X plus 2 y's plus 0 z's plus 3 w's is 7. And x's and w's, y and w's are the open variables. Y's and w's. Bring it to the other side. So you get x is equal to 7 minus 2y minus 3w. The second equation, it says 1z plus 4w's is 2. W, oh, that's an open variable. Z is not. Z has a check mark by it, just like X does. They had a leading 1 below them. A variable or a column that does not have a leading 1 is an open variable. Z is 2 minus 4w. But remember, we're calling, I'll write it down here, we're calling y, the letter r, so it's 7 minus 2r minus, and the w we're calling s. W is s. So z is 2 minus 4w, but w is s. Okay, so I have my 4 answers. X is equal to 7 minus 2r minus 3s's. Y equals r. Z is equal to 2 minus 4s. And w is s. So there's an answer. You might want to write it as follows. You have, well, you can write it in matrix form. X, Y, Z, W. It equals to just regular numbers plus, well, let me leave space so I can fix it at the end, plus some R's, and then plus some S's. So X is the number 7 minus 2 R's plus negative 3 S's. Remember, this is the same as 7 plus negative 2R plus negative 3 S's. And Y is just R. It's 0, it's 1R, and no S's. Z is 2 minus 4 S's. Has no R's. But you add negative 4 S's. That's Z. And W is just S. No regular constant number. No R's for 1S. Now, scalar multiplication. In this second matrix on the right-hand side, they all have R's in front of them. While they're all being multiplied by R. You could factor out the R. You can factor out the R. Plus R. And since it doesn't look so neat, I'll just write it down again. X has negative 2 R's, Y has 1 R, Z has no R's, and W has no R's. The last matrix, they all have an S. You can factor out that S. And there is your answer. X is equal to 7 plus 2 minus 2R minus 3Z's. Y is 0 plus 1R plus no S's. That is, Y is just R. Z is 2 plus no S's, no R's, minus 4 S's. Z is 2 minus 4 S's. W is 0 plus 0R plus 1S. That is, W is S. And yes, you need to be able to read that off. Here is a very nice example. You need to be able to go to that top left row reduced echelon or reduced row echelon form augmented matrix and write down the solution, even if there are open variables. Okay. That completes this section. And now we want to do one more. We want to talk about one more. We want to talk about homogeneous systems. To solve a homogeneous system, everything is done exactly the same way. Not anything different. Not anything differently. Now, why the special name? The answer is because the right-hand numbers are all 0. The right-hand numbers are all 0. But how you solve it is exactly the same. A homogeneous system is a system of linear equations whose right-hand side numbers are all 0. Maybe you'll have x plus y plus z plus w is 0. That's the right-hand number. And x plus w is 0. And x plus 2y plus z is equal to 0. If you were to make up the matrix, the numbers in front of x's are all 1s. The numbers in front of y's are 1, 0, 2. In front of z is 1, 0, 1. In front of w is 1, 1, 0. And the right-hand side is 0. Okay. Now, just to comment, if I multiply any of these rows by 11, say the second row, if I multiply it by 11, you know what? That number won't change. It'll stay 0. If I interchange row 1 and row 3, or any rows, the right-hand numbers will still be 0. If I take 10 times the first row and add it to the second row, well, 10 times 0 is 0. And when I add it to the second row, which has a 0, that right-hand side will stay 0. It will never, ever deviate from 0. Now, if you were to reduce this, and like I just said, I bet my life on it, the right-hand side will still be zeros. If you were to reduce this, which I actually worked out, I just don't want to formally do it again, you get this. Row 1 has a leading entry, a leading 0. Row 2 has a leading 0. Row 3 has a leading 0. Okay? Now, the leading 0 in row 1 does not have to be in column 1. The leading 1 in row 2 does not have to be in column 2. The leading 0 in row 3 did not have to be column 3. When it comes to column 1, I see a leading 1. Column 2, I see a leading 1. Right there. Column 3, yep, there's a leading 1 in column 3. Column 4 does not have 1. Remember, the variables were x, y, z, and w. W is an open variable. The first line says that x plus w is 0. The second line says y minus w is 0. The third line says z plus W is 0. Well, if we say that W is R, any real number, well, this says X is negative, bring this over, is negative W. But for W I put R. This says that Y is equal to positive W, which is R. And Z is negative W, negative R. And there is your solution. You know, if X is 3, if R is 3, negative 3, 3, negative 3, W is 3. If W is 0, if R is 0, then all 4 entries 0 work. If R is negative 5, you'll get 5, negative 5, 5, and negative 5. This solution will satisfy all 3 equations. So will that solution. So will that solution. As long as X and Z are the same, and Y and Z are just negative, Y and W are negative what X and Z are. And after all, X and Z are equal, and Y and W are equal, but their signs are different. That is, X and Z have one sign, like positive, and Y and W, they just have a different sign, negative 5. Okay. So now we go on to the theoretical exercises. If you want to learn linear algebra fairly well, this is what you have to be able to do. To be honest, if you don't know how to do the theoretical exercises, you don't know linear algebra. If you just know the mechanics, well, you don't know anything of real value because the computer can do the mechanical work. Okay, nobody needs for you to row reduce a matrix because the computer can actually do it because there's an algorithm. All right. Now here's a very interesting fact about homogeneous solutions. Let AX equal B. Generally, you put a bar over the X because it's a vector. It's a column vector. So you even put one over the B. All right. Okay. Suppose U and V are solutions to AX equals B. That is, A times U will equal B, and A times V will equal B. Oops, I have one mistake. This is supposed to be a homogeneous solution system. AX equals 0. It's not the number 0, it's the 0 vector. You know, 3, 1, 2, 1, 2, 8, 2, 1, 4 times X, which is X, Y, Z. So this is capital A, this is capital X, and it is to equal 0, 0, 0, which is the 0 vector. Okay, what we have is really beautiful. If you have two solutions, the sum is going to be a solution. Because unlike most other numbers, 5 plus 5 is not 5, and negative 3 plus negative 3 is not negative 3. But you know what? 0 plus 0 is 0. So we want to show that given that u and v are solutions, we want to show that u plus v is a solution, u minus v is a solution, and we're building up. I want to show that r times v is a solution, where r is any real number, and here it is. R times u plus s times v is a solution. R and s are any real numbers. The last one is said to be a linear combination of u and v. What does that mean? That's called coming attractions. All right, so a times u plus v. Now, u and v are matrices. Whether they're 1 by n matrices or n by 1 matrices or 4 by 3 matrices, they're matrices. And so is a matrix. And we learned that matrix distributes. Plus, you can distribute like this. And we are told that u and v are solutions. That is, if you plug in u, a times u will give you 0. And if you plug in v, a times v will give you 0. Oh, you mean that's the 0 vector? Plus, that's the 0 vector? Well, if you add the 0 vectors, say it's in R3, or it's 3-dimensional. 1 by 3. Sorry, 3 by 1. If you add this, you get back the 0 vector. A times u minus v. That's what I claim x can be. X is the placeholder for the solution. I'm claiming u minus v is a solution. Well, just like before we distribute. We get au minus av. We get the 0 vector minus the 0 vector, which is the 0 vector. A times anything that gives you 0 is a solution. Now, what about a times RV? You need to remember the theorems that we went over. The scalar can come out in front. This is R times AV. But V is a solution to AX equals 0. That is, AV is 0. And, you know, if you scale the 0 vector by 3 or R, you get back the 0 vector. This is still the 0 vector. What about A times RU plus SV? This is the one, in my opinion, that makes all this stuff really beautiful. It's like, wow. So if you have two solutions, even one solution to a homogeneous problem, you have infinitely many. Just remember, if AX is 0 and you have a solution, you know that AU is 0. Well, let's suppose you have a non-trivial solution. You have a solution other than the 0 vector. U is not the 0 vector. But if AU equals 0, well then there's others. 3U is different than U. And this also equals a 0 vector. And A times 4U is the solution. And A times negative 3 over 8 times U is the solution. Any multiple, if U is a solution, or if V is a solution, we show that RV is also a solution. Okay, now let's do the last one. We can distribute. We get A times the first vector, RU, plus, because it says plus, a times the second vector, which is SV. But now, in this first product, we can pull out the scalar. We get r times AU plus, here we can pull out the scalar. We get S times AU. And the next few seconds, you'll see it all come together. It will all come together in the next moment. We have S times AV. But AU is 0, because U is a solution. You get R times the 0 vector, plus S times AV. But V is a solution to the very, very top equation, AX equals 0. So AV is 0. And R times 0 vector is a 0 vector, plus another 0 vector. Look at that. We got the 0 vector. If U and V are solutions, then any multiple of U plus any multiple of V is also a solution. And that's pretty neat. So if you have a non-trivial solution, you have infinitely many solutions. Now, let me just be clear what I mean when I say a non-trivial solution. In particular, let me show you what a trivial solution is. If you have a matrix A and you multiply it by X and you get the 0 vector, that is, you have 3, 1, 2, 4, 0, 5, 1, 2, 8. And you multiply it by X, which is X, Y, Z, and you want to get 0, 0, 0. Well, the trivial solution is, oh, you want to get 0, 0, 0? Why not just let X equal 0, 0, 0? After all, 3 times 0 is 0, 1 times 0 is 0, and 2 times 0 is 0. That is, row 1 dotted with that column is 0. And then if you dot row 2, 4, 0, 5 with 0, 0, 0, you're going to get 0. 4 times 0 is 0. 0 times 0 is 0. 5 times 0 is 0. You get 0. Same thing with 1, 2, 5. You dot it with the 0 vector, you're going to get 0. So 0 is a trivial solution. And if 0 is the only solution, if 0 is a solution, you cannot use this vector 0 to find other solutions. You can't, because you can't do r times 0, 0, 0. I mean, you can, but r times 0 is 0, r times 0 is 0. You don't generate a different solution. You didn't generate another solution. Okay. Now, what if, and this is the big what if, because I have no idea if what I'm going to say is right or not. It will be highly unlikely this is true, but it's just theory that we're talking about. If it turned out that this matrix times 1, 0, 4 equals 0, 0, 0, that is, X equals 1, 0, 4 is a solution, well, that's a non-trivial solution. And once you have a non-trivial solution, you can generate a whole host of other solutions. 1, 0, 4 is a solution. Multiply it by 3, and that's another solution. Multiply 1, 0, 4 by negative 2, negative 2, 0, negative 8. That's another solution. you can generate many, many solutions by that last theorem that we proved. We proved that if U, let this be U, we proved that if U is a solution to a homogeneous system of equations, then 3 times U is a solution. Now, one last thing I want to show you, and then we'll be done. This is not true if it's a non-homogeneous system. That is, you have AX equals B, but B is not 0. If B is not 0, then it is a non-homogeneous solution. So you have AX equals B, and B is not the 0 vector. Okay? Suppose U and V are solutions. Okay? Suppose U and V are solutions. That is, AU does equal to B, and AV does equal to B. Well, for the sum, it won't work. Because you do get AU plus AV. But there's one problem with that. AU is B plus AV is B. This is equal to 2B, which is not B. For this to be a solution, A times that should equal B, but it doesn't. Now, while we're here, let's go a little bit further. Let's go a little bit further. Let us go a drop further. Okay. Let U be a solution to AX equals B, and V be a solution to the corresponding homogeneous system. That is the same A times X, except it equals 0. I claim that U plus V will be a solution. U plus V will be a solution. Since I wrote on it, it no longer looks like U and V. Vector U, vector V. Okay. So A times U plus V. This is A times U plus AV plus A times V. Well, we know we know U is a solution to AX equal B. That is, A times U equal to B. Okay, so we get B plus AV. Well, V is a solution to this. That implies AV is equal to 0 vector. And B plus the 0 vector is B. Well, A times anything that gives you back B is a solution to AX equals B. So, U, a solution to AX equals B, plus V, which is a solution to the corresponding homogeneous system. That is AX equals 0. Is a solution to AX equals B. So, if you have a solution to AX equals B, and you have a solution to AX equals 0, then their sum will also be a solution. And you know what? So will their difference. Because B minus 0 vector is still B. So U plus or minus V is the solution to AX equals B. Okay, that completes this section. Study hard.